Okay, so far what we've talked about has been and we've made the point that our interest so far has been applying this to scalar variables, pressure or head, um, concentration, and temperature. So components that have magnitude but no direction, and they only have a single degree of freedom per node as a result of that. You might recall that when we started talking about one-dimensional elements, we could develop the equations for a finite element, a one-dimensional two-node finite element, just by writing Darcy's law along the length of a pipe, and split the partial derivative dh dx into two parts, one which was the upstream head minus the downstream head, divided by the length of which it occurred, L in our case. And if we did that and wrote Darcy's law without consideration of the fact that Darcy's law really is a vectoral component, right? We use Darcy's law and we write it typically as velocity is equal to minus k dh dx, either as a partial or a full derivative. This, by definition, is a velocity and it's in the x direction. And so the reason for this negative sign in Darcy's law is because it flows in the opposite direction. So if you think of a porous medium that happens to be sitting in the next direction there and with head drawn vertically, and you think about a groundwater table, for instance, then we know that for this, the gradient here, delta x delta h, would give us a velocity in the positive x direction, but this is a negative gradient. And so that's just the reason for that. And so the way we got around it when we did this for a single two-noded element was that we said that the flow into or out of each of these nodes, we're not going to define as a direction, but only as a binary choice. One, it's in or it's out. So it could be either negative or positive depending on whether the flow rate was in or out. And so that's how we were able to develop this conductance matrix, which if we look back on it now, basically allowed us to say that flow rates were related to nodal values of heads through a conductance matrix, and that conductance matrix actually did conform, as we could show it now, as something that looks like this, which we've seen many times also. Right? And so that was our simplification in dealing with this. We took this scalar quantity and we just said in or out, negative or positive, and then the magnitude defines the flux. So now that we've talked about all of those, it's time for us to move to the next level, and that is to be able to start looking at problems which involve vectoral quantities. And so those might include solid mechanics for sure, because that's really what we'd like to get to as well. But on the journey to look at that, maybe it's useful to take just one period and talk a little bit about trying to solve another set of equations, which are the Navier-Stokes equations. And so typically what happens in groundwater flow, we know that the simplification that we take is that, well, we know exactly what we do in groundwater flow, right? We write a partial differential equation, which is basically dv dx plus dv dy equals 0. And into this, we inject Darcy's law. V is equal to, we can write it in terms of heads, or we can write it in terms of pressures, doesn't really matter. Negative, I suppose, goes in here. And so this is where our second order PDE comes from, which is ultimately kx d2h dx squared plus ky d2h dy squared equals 0. And so that's the equation that's typically used for groundwater flow. And you'll note two things. We've all said that when we develop these finite element equations, we rely on maybe three principles. We have a conservation equation. We require that the variables in the system are continuous. There's no discontinuities. And we have a constitutive equation. So in this particular case, our continuity equation is conservation of mass. This is just saying mass in equals mass out. And the constitutive equation is Darcy's law, which links the velocities in this equation to some other variable, which is his head. And so in this, we satisfy continuity, and we use a constitutive law which accommodates the fact that we have viscous losses in the system. So when fluid flows from upstream to downstream, there's a certain amount of energy that's used up in that it's not reversible, and that energy is because the viscosity within the fluid shears past the grains within the pores, which it is flowing around. And so this, if you like, is our surrogate for dealing with frictional losses within the system, The other way to solve problems is to use a characterization that doesn't make this simplification that we can approximate these frictional losses within the system. And that approach uses the idea that we will balance momentum. And so that's why this is maybe strangely referred to as momentum transport in here. Because what we're doing is the Navier-Stokes equations come from solving a much more basic condition, and that is that we satisfy momentum within the system. And momentum really, if we wanted to write it out, momentum is really just satisfying F equals ma. Forces and accelerations in a three-dimensional system there are three of them, right? Forces in x, y, and z. And so you'd expect that we'd have three conservation equations. In addition to that, figuring out what other components we need. And so I'm not sure that in this I developed the equations. I'm not sure it really matters. But what we'll find is that we end up with a set of three equations which represent conservation of momentum, which look like this, which we'll scroll to a little later. And we'll see that these expressions have within them some variables. And these variables would be velocities. And if we have behavior in three directions, and accelerations in three directions, and forces in three directions, then equally we have velocities in three directions. So we'd have, you see this is slightly bold here. This is actually velocities x, y, and z. Forces would be the body forces which are applied to our system, which would be the unit weight of the fluid, which is a known. This is a velocity, this is a viscosity, and we have another component which is the fluid pressure at a point. And so if we have three magnitudes of velocities and one magnitude of pressure, but we only have three equations in 3D, then we need another equation to be able to close the set of equations. And typically, not typically, but the way we do that is by adding another equation, which is continuity, which is basically this equation, actually. It's exactly this equation, which if it was, this would be x, this would be y, and there would actually be another term on it if it was in three directions for velocity in the z direction. And so with that, we have 1, 2, 3, 4 unknowns. We have four equations, and we can solve it. And so that's the set of equations that are specifically solving for momentum within our system. If we solve things using the so-called groundwater equation, or for porous media flow in petroleum engineering using pressures, there is no conservation of momentum in that. And the assumption is that rather than momentum, this term here being important, which it isn't, what is important is the conservation of forces, and the forces are due to viscous losses. And the viscous losses come through Darcy's law. And so that's the difference between those systems. So you can't use Darcy's law to solve open channel flow problems, for instance, because it's not going through a porous medium, it's sitting on its own, and so you could imagine that there is really no concept of Darcy's law that you could apply in that particular case. So momentum transport is where we solve for the system of equations without Darcy's law, and actually, as a consequence, take care of the changes in momentum within the system. So there's a long reader about this, which is a chapter out of Zienkiewicz's book, maybe what I often refer to, maybe a bit too irreverent and hopefully not blasphemous, as the finite element Bible, but it is really a very well, it's a classic book, I think, by someone who's not long been dead, but who was a giant in the field. Don't know why it got blurry there. And so what I wanted to do today was talk about Navier-Stokes equations, not derive them, but talk about them in a physical sense as to what they are, and then talk about how we might solve them using finite element methods. Not by going back to some first principles and deriving the finite element equations for them, but by doing it by inference, if you like, by heuristics, based on what we know about zeroth order, first order, and second order equations, and looking within Navier-Stokes as to where those individual components exist. So that's what we'll attempt to. And then I want to use EGEEfem to put it together, and then to solve a simple equation, and to again reinforce, if you like, the fact that if you ever develop codes, or even if you use codes, you should always make sure that they actually satisfy a very simple problem that means that you have some confidence in whatever the code is doing. Okay. So we can write Navier-Stokes equations in a variety of different ways, either in tensor notation or in more an expanded vector notation. This is the form of the equations which we defined before, of which there are three equations because there are three values of velocity, which I've called Vx, Vy, and Vz, which will exist in there. And as we mentioned before, this is a body force. So I suppose you could imagine that if you have a little differential element that represents this system, then there is a force, if this is the x, and this is the y, and this is the z, which would be a right-hand rule, right? X, Y, Z. Then the force applied to this element would be a force in the x direction, or a force in the z direction. And so, in the same way, this would have components fx, fy, and fz. And you could imagine that fz, for instance, you might want to include as being equal to the volume of the element multiplied by density, which is just the body force due to self-weight, which would in this case be the size of the element, dy dz, times density. So that's the use of this term. This is the fluid pressure gradient that's applied as you go. So it would have within here, it would also have a fluid pressure. One variable, not bolded, as you see here. And these velocities would be three components. This is viscosity, fluid viscosity. And this is density. So we've seen that before. And so what you could think of is that this, you could also think about writing this equation. If I do this, this is an equal sign, that this is sum of the forces times density. And in our terminology, this would be displacements dot dot, right? This is U for displacement. That's what we'll use later on in the course. Or rate of change of velocity is an acceleration. d2u dt squared is also the same thing, right? So d2u dt squared. And so you can think of this as being this is the MA term. This is a mass times an acceleration. Or actually, so if you look at the units of this, it's actually all of the units in the equation have to be the same units. And so it's actually a mass per unit volume, because density is kilograms per volume. And so it's if you think of it, it's a body force per unit volume of this that we're talking about. So all of these terms are body force per unit volume. And you can look at the units. This force has to be a body force per unit volume. So it wouldn't actually be this. It would actually be what would it be? It would actually be, yeah, it would be right. It would be the product of these two. So this would be a density, which is and this would be a volume. So volume times a density is a mass. So this would end up being, I guess, yes, that's right, isn't it? G. So it would be a force that results from this, and it would be a force for a unit volume of the system. Likewise, if you look at the magnitude of pressure, then pressure is going to be equal to pressure gradient. If you look at the units of this, then pressure is in newtons per meter squared times meters for this, then newtons per meter cubed. So force per unit volume. So we can think of that. So this is inertial force per unit volume. This is a body force per unit volume. This is a pressure force per unit volume. And this would be a viscous resistance force per unit volume. And you could do the same, I guess, just to check the units on this, right? So if we did this, and the units would be d2v dx squared. This operator here is just this. And so if you look at the individual units of that, we know that viscosity is Pascal seconds, which is newtons per meter squared, which is a Pascal, times seconds. Okay, I'm just trying to work out where the this is. Oh yeah, I was wondering how this is going to get cancelled out. Velocity is in units of meters per second, and then the derivative is 1 over meters squared. This is x squared, so we don't care about the derivatives, but this becomes this. And so if we get rid of the terms, seconds, this is meters fourth over meters, and so this is also newtons per meter cubed. So same thing. So this is a viscous resistance, if you like, that results from this. Not by going past porous media, but by going past the blocks that are above it and below it, basically. That's what's going on. Okay. So if we expand that out for these three equations, then they look like this. These are actually three velocities, which we have here. And these are three velocities which we have here in this term here. So if we expand it out, we end up with one equation. I could draw a line through this, which would be the top part. Once you've done these multiplications on this, you'd end up with those terms, but you'd end up with three equations. And we've made the point that we have 1, 2, 3 unknowns in velocity and one unknown in pressure. So instead of three equations, we actually need a fourth to be able to close the system of equations. If we want to reduce it from three dimensions to two, then we would just get rid of the z direction and have it flowing in the x and y plane, however we want to orient it, either horizontally or vertically. And if that's the case, then we can just get rid of all the terms that involve z, such as, for instance, this, and this, and this, and this, and this. Because clearly, the assumption is the velocities are only within this plane, xy plane. So the velocity in the z direction, by definition, has to be 0. So it seems reasonable that we can drop that out. And I guess the other terms that will turn up in that would be terms, for instance, that get multiplied through, I guess it will always be, I guess there will be a term which operates on Vz. This term here, the rate of change of velocities in these directions would be 0 as well. So in other words, if you imagine flow within this horizontal plane, which is my thumb and my first finger, then any picture of flow within this plane will be repeated in any planes that are adjacent to it. So the gradients of velocities, or the pressure gradients as you go up in the z direction, will be uniformly 0. And so the pressure gradients here, by definition, have to be 0 on this. And so it turns out that the system of equations that we'd end up, if you wrote this out in longhand, will look something like this. And again, we have two unknowns, a velocity in x and a velocity in y, in each of these terms. Velocities in x and y, and a pressure. So we have three unknowns, two velocities, one pressure, so we need three equations. Two momentum balance equations and one continuity equation. So that's what we start off with. So we could try and solve these equations. So if we go down from this 5 and 6 here, you see them repeated here. I think it's no different. And so what you notice is that if they're written out in this way, they exist in a variety of different forms, right? So these are first order equations, things like dc dx. So remember, we have equations that look like dc dt, which vary with time but not with space, which we've called zeroth order. We have those that vary with space to the first order, and we have expressions that vary with space to the second order. And so if you look through here, we have some that look like first order ones here, first order again, and also second order. And so what we're going to do is we're going to see if we can, since we know exactly what the finite element equations look like for these relationships, we could try just by substitution in terms of what we think we want to put in there. We should be able to work out exactly what we can substitute into to represent these equations, because we know, for instance, that this equation looks something like what? Integral A transpose dA dV times C, right, for this. And so we know absolutely this form. We know that this is what we've called before K2, not the mountain. So we have first order terms, and we have second order terms. And in these cases, we've thrown away the acceleration terms. So I guess that's fine. So I guess the other thing that I've done here is I've got rid of this. So the inertial terms I've thrown away, just to make our lives a bit easier. So they don't turn up here, and they don't turn up on the next equation. So, so if we look at the advection dispersion equation, we recall that this is what we're representing. The first order term, which is the one that's difficult to deal with, exists here. The second order term, which is less difficult to deal with, exists here. And this zeroth order term exists here. And so what we could do is we could try now solving this system of equations. So what we're going to do is we're going to solve for what is referred to as Stokes flow. And Stokes flow is just where density goes to 0. So in other words, it's the case where we drop out these first terms. It's really saying that, I guess in this term, there are two accelerations in this. There's an acceleration due to the fact that a particle of fluid is changing its velocity with time at a particular location. But there's also an acceleration referred to as the convective acceleration, where a particle, so in other words, if you take a snapshot of a flow field at a given time, and you look at a particular point, and you see that that velocity at that particular point, not the particle that's flowing through it, but at that particular point changes with time, then you have a term that represents dV v dt. Right? That's a regular acceleration. If you, at a particular point, if you take that and, for instance, you multiply this by, for instance, dx dx, which you haven't changed anything, then what you have is something that you could write out as being a, this term here, change in the x location with time is what? It's a velocity in the x direction. And this other term is a change in velocity with space. And so if you take this derivative, which originally was dv dt, you can write it into something that isn't changing with time, but is physically changing with space. That's exactly what you have here. These terms are all changing with space. So you have this idea of, one, you take a snapshot at this point. If it changes its velocity from time 1 to time 2, then this term means that its velocity is changing. It's not steady state. But if it's steady state, so if you take a picture of the velocity profile at time 1 and you take it again at time 2 and all the vectors look exactly the same in that frame, it doesn't mean that this term is not 0. Because, I'm laughing because something, my phone's buzzing in my pocket. But because in going from A to B, it actually has to either accelerate or decelerate because it's changing velocity. And so to change velocity, you have to provide a force to be able to move it. And so that's part of this change in force balance. And so what we're doing is we're getting rid of both the non-steady part of this, but we're also going to kill the convective acceleration, which is a steady state part. So we're just getting rid of these, just to make our life easy. So that's what becomes Stokes flow. So Stokes flow 1 is steady state because it doesn't have this dv dt term in, and it's also for cases when the density goes to 0, which is merely saying that maybe it's molasses that is flowing. The velocity is very small, therefore most of the energy that's lost in going from A to B is taken up by the viscosity of that, not by the fact that we have to accelerate it, which would be the case if I took a balloon full of water and threw it across the room. Different things, right? So if we take Stokes flow and get rid of the stuff on the left-hand side, we're left only with the material on the right-hand side. And so we'd only have these terms, basically, that are outlined here. And this terms as well. So those are the terms that we're left with. So what we could do is we could rewrite these 3 equations. I guess I should leave both sets of equations on. So this one here is here. So we have a force, which I've taken over here. We have a first order term operating on pressure, which I've written here. So the Roman 1 means it's first order, and this is our conductance matrix. So this is the FEM statement, FE statement. And it operates in the x direction, so this x is here. And if we look at these terms which represent the viscous losses in the system, we have a change they're both due to flows in the x direction, but they're due to a gradient in both x and in y. And so this is the term that represents that, but they only actually operate on velocities in the x direction, this one here. Right? So take that on trust. The second equation, take F to the left-hand side. We have a force, again, here. We have a first-order term for pressure, which is a scalar variable operated on as a change in the y direction. This term here is now with respect to y instead of x. And these now operate, instead of operating on x, they operate on y. And again, it's a second-order equation that defines that behavior. This is this second-order PDE that we've dealt with before. So that's kind of the rationale of what we're doing. And finally, the continuity equation, first order, and it operates both on x and y. And so if we write this down here at the bottom, you see here, it operates both on x and y as a dependent variable. And it's the first order equation, dv dx and dv dy. So it's this first order. And it operates on the x. It's with respect to x, which is what this x is here. And it's with respect to y, which is this y here. And the t is just the transpose because of it has to be that way to be able to fit it in. So all we've done is we've taken these equations and we've figured out we have first order terms and second order terms and how we split it up between the things that they operate on. There are three equations, there are three nodal variables, velocity in the x direction, velocity in the y direction, and the fluid pressure. And we have this expression that really honors those finite element equations. In the same thing that we did with when we first derived the conductance relationship for finite elements for a one-dimensional porous media flow node, we split this now into nodal variables. So these now would be nodal variables of pressure, velocity in x and velocity in y. So we can think of these as being vectors that operate on matrices, and these would also be vectors as well. And so if we try and split them out into a 3x3 matrix, which is what we're going to want to come up with, right? A 3x3 matrix that includes locations for 9 locations, right? And so what we're going to try and do is we'll take out the variables from here. Well, this is just expanding a little bit. This is just this same system of equations written with an extra space. With this just moved over here. Right here. So I think you see what's going on in this. So these are all vectors. And now once we have that, well, I could just as easily have done this, I guess, on here. Right? These are forces. I guess I can't quite do it because these terms have to go into a vector. So if you take the dependent variables out and you put them in here, then you end up with a matrix equation which describes our system. Haven't derived anything, but we do know what these individual matrix terms are going to look like. This term here is going to look like what? This is going to be K1, and I'm trying to remember exactly what it looks like. I think it looks like shape functions times A times over V multiplied through by velocity. We had a velocity in the middle before, but I've taken the actually it's not a velocity on the outside. This is what the K matrix looks like. And it would operate on a fluid pressure. Because you note that the equation that we had before was something that was V dc dx, and the equation actually looked like B transposed VA dV. If this term is equal to 1, then this term is equal to 1, and therefore we don't need to deal with it there. So that's basically what we're doing. And so we should know exactly what these terms are that inhabit this. It'll be the same term kind of that inhabits this. But what we'll do to make these slightly different, maybe on the next page, no, it's not on the next page, is that you'll recall that if we had a vector which was something like minus Vx dc dx minus Vy dc dy. So you'll recall that you may recall that the finite element statement for that was something like this integral B transposed and I'll write V out in terms of both x and y, because both terms went in there, multiplied by a. And I guess it would operate on a concentration. And so if we wanted to make this equation only represent minus, for instance, if we wanted it to represent minus 1 times dc dx minus 0, which is what this term is, this is the derivative only with respect to x, then we could do that just by making vy equal to 0 and vx equal to 1. Likewise, when we have these second order terms that populate this, I guess we don't have to do it for that. We have the second order terms which operate on both. No, I don't need to do that. So in other words, we can manipulate it to get the right matrix expression out of this. And this, of course, in this particular case, this would be K1x. Because it only relies on the component which is the derivative with respect to x. It doesn't include this, not because we've excluded it, but we've put the multiplier here equal to 0, and so it just drops out as a function. And so that's, it seems that so that's what we could do. So what we could do is we could try and put together a system of equations that, where this was the K matrix, this is our quote-unquote K matrix, and it is, if we write this out in longhand, it is F equals Ku. Not so different from what we've talked about before. This would be for a single element. These would be not displacements, but they would be velocities, and it would also include the pressure, be the so-called solution vector. And these would be the body forces which we have in our system as well. And this would be the matrix which we have to make up of these submatrices. So these are individual matrices, and the size of these matrices will depend on the particular shape of the element that we include. Okay? So let's figure out how we might go about doing that. All right, so what I'm going to do is I want to put together a solution for this system using what we've done so far. And so we have to decide on a geometry that we want to represent. And one geometry that we could represent is trying to represent flow between two parallel plates. If you look at flow within a fracture or within a duct, it's between two parallel plates that are separated by some aperture or opening. Then the solution to that system of equations is pretty straightforward. You get a parabolic velocity profile where the fastest flow is in the middle, the slowest flow is at 0 where it contacts the plate, where it's actually, you can imagine it as being attached to the static plate, so the velocity is 0. And the solution for that is this. The velocity in the x direction is conditioned by the viscosity, the pressure gradient between the upstream and downstream, dp dx as you go downstream. So you can imagine this being a conduit which is upstream or downstream. If you looked, by the way, at the velocity profile upstream, it would be identical to this. And the reason, so then clearly if it's steady state, it would look identical at this point here, at all times that you took a picture at. If the velocity downstream is identically equal to the velocity upstream, then clearly as you're going up from upstream to downstream, there's no convective acceleration. It's not going at one velocity here and a different one here, in which case it has to accelerate and has to work against inertia. There is no convective acceleration in the system. So the only loss in the system is due to viscosity. And so you can think of this, the best analog I think is to think of a deck of cards where you shuffle them over each other. They all shear relative to each other. And this shearing between all of these lamellae is the action of viscosity that builds up this force that you have to apply. So the force that you're applying due to the pressure upstream relative to pressure downstream is all being expended in terms of viscous loss and through this equation. So this is the expression for velocity in terms of the coordinates. This is a plot of what it would be if this was the bottom boundary here, and if this was the center line here. So in other words, the coordinate system for this is that this is the axis x, this is y equals 0, this point here. And if that's the case, you can choose y to be positive or negative in either direction. Then if you place y equals b, which would be this point here, then this term here is equal to 0, and you get 0 velocity. If you place y equals 0, then it's minus b squared over here, and you have the maximum velocity at this point. So choose a dimension. I don't know why it doesn't, why it gets blurred here. So this is the geometry we're going to solve for. If we want to solve for it, then we want to put some finite elements in there. So I'm going to put these elements that make up this geometry here. And because we know how to do it, I think we know how to do it, we'll use triangle elements. And then what else do we need to do? I guess we need to think about what the boundary conditions would be. And so what would the boundary conditions be that we put on here? So each of our finite elements, if we take, for instance, this top one, have nodes attached to them. I don't know why I did this, but that seems strange. It doesn't matter. So it'll have a velocity in the x direction at each node. It would have a velocity in the y direction at each node. And it would have a fluid pressure at each node. Those are the three conditions that we have. If we look anywhere within this duct, at any point there'd be an x and a y flow velocity and there'd be a pressure. And we know that because these are the equations that we've dealt with, these three equations. Velocity x, velocity y, and pressure. And so those are going to be the nodal variables. Don't know why it wants to be blurry, but it does. And so what we can do is we can discretize elements to put in here, but also we could talk about what the boundary conditions would be. So what the boundary conditions are is we're taking a portion of this duct, maybe I can draw it right above it. And these correspond with these two sides here. We have an upstream pressure which is equal to 1, whatever the units are. And we'd have a downstream pressure equal to 0, which is just saying that this pressure gradient is what happens between upstream and downstream. That's what's driving flow. And we need to figure out what the boundary conditions would be in terms of these other components. This would be a boundary. We're representing half geometry, just to make life easy for us. So this bottom boundary is closed. So we know that the velocity in the y direction has to equal 0 across here, right? By definition. This, if you like, is a line of symmetry. Actually, all of these are lines of symmetry. But we only have to impose this top one. If you, from continuity, if you drew a little stream tube, you know that all the fluid that starts off here ends up down here, so it can't be flowing in the vertical direction. So by that reasoning, the velocity in the y direction has to be 0. Actually, it's 0 everywhere, but certainly it's 0 in the y direction along this center line, because that's a line of symmetry. And so the velocity here is also 0. So Vy equals 0. And so what we'll want to do is be able to define a boundary condition for each one of these terms. So, well, actually, why don't I do it by drawing first the ones, maybe the ones we know. So we know that pressure here is equal to 1. So maybe I'll just outline this. So the pressure at each of these nodes is equal to 1, so we know that. The downstream condition, very simple condition. And of course, we might want to do a whole bunch of other elements rather than this simple geometry. We know that downstream, the pressure is equal to 0, which is this term here. So we know all the pressure conditions within the system. We don't have any pressures to solve for. What about our velocities? We know that Vy equals 0 here. We know that Vy is equal to 0 here. We know that Vy is equal to 0 here, for what we said before. And we know that Vy, interesting that it does this. Imagine that Vy is equal to 0 there. It doesn't want to write it. So those are the conditions that we know. The conditions we don't know, well, some of them we do. What's the velocity in the x direction here? We've said that as a boundary condition, it's stuck to the wall, so actually Vx here is equal to 0 too. And by inference, Vx will be equal to 0 here as well. And so what that leaves us then are the conditions that we don't know and would like to find out. We'd like to know what this is. We'd like to know what this is. We'd like to know what this is and this is. And also these two. And these two. It won't let me write it. But if you're keeping up with me, you can do it. So I'll do it on the lower one. The ones we want to know are all of the x direction velocities. Oh no, that's right. I violated my rule. We don't need to know these. These are boundary conditions. We need to know these. We need to know these. We don't need to know those velocities. And I guess we also need to, these will be 0 by definition, but we can solve for these because they're not part of the boundary. So it appears that in this system, if we discretize it like this, we have 1, 2, 3, 4, 5, 6 nodes and 4 elements. We know that each node we have 3 degrees of freedom. So we have 6 nodes times 3 nodal degrees of freedom, which equals 18. So we have 18 equations that we'll want to solve. But the number of unknowns that we have is only going to be 1, 2, 3, 4, 5, 6 unknowns. So in other words, we'll start off with a system of 18 equations. We'll manipulate it. That system of 18 equations will look something like F equals K U, where these are velocities. But although there's 18 equations, we'll end up only solving 6 of them after we manipulate them. Okay. All right. What else do I need to say? No, that's it. That's fine. All right. So let's figure out exactly how we might do this and how much time we have. Maybe it's worthwhile. I think actually I'll do this. I could go to the EGEEfem file, but instead I'll do it here because it's larger and you can see it. And so this is the system of equations that we're trying to solve. And the other thing that we need to reckon on, well, I'm going to put it back in green for some reason. So this is a system of equations that we're trying to solve. So this is convenient to think about it this way because we can think, of course, that if we look at the forces in the x direction, which would be present on 3 nodes. So remember, we number these forces in the x direction at node 1, forces in the x direction at node 2, and forces in the x direction at node 3, that would give us F1, F2, F3, which is in the x direction, which should be this term here. And it operates on some vector, or matrix rather, which must have 9 terms in it, which will be integral A transposed dA dV, where this term here actually will just be 1s. And it operates on velocities at each of these nodes. The velocity at node 1 in the x direction, the velocity at node 2 in the x direction, and the velocity at node 3 in the x direction. And so we know how to do this. All of the problems we've dealt with so far have been scalar problems. They have a magnitude at the node, but we don't care what its direction is. These have direction, but we don't care. So this happens to be a magnitude of velocity at node 1, a magnitude of velocity at node 2, and a magnitude at node 3. So we can write this as basically an element relationship which defines this behavior for this point. And that's exactly how it looks like in this relationship. This, and this, and this. Forgetting this term, right? But when we solve the system of equations, we don't solve it this way. When we solve the system of equations, it might be worthwhile writing it out. I can do something like this. When we solve the system of equations, we do this. Bless you. We know that we number these counterclockwise. We know that we have, at each node, we have a force in the x direction at node 2 and a force in the y direction at node 2, and also a velocity in the x direction at node 2 and a velocity in the y direction at node 2, and a pressure. So this is so we have pressures and velocities. So one pressure, 2 velocities, which are equivalent to, not yet, forget it. I was going to forget about the forces for now. And so we have each of these 3 degrees of freedom per node. When we write the equations that describe the system, because we write them on a node-by-node basis, what we will do is we would like to write our variables as our matrix. So 3 degrees of freedom here, 3 degrees of freedom here, and 3 here. So it's going to be a 9 by 9 matrix. I won't write out that full matrix, but I'll make a stab at what size it would be. So this is some 9 by 9 matrix. And it operates on, if I can draw the vector properly, 9 nodal variables. And what we had before, this leads us to think that we'd have velocities in the x direction at nodes 1, 2, and 3 as 3 components, velocities in the y direction at 3 nodes as 3 components, and then pressures at nodes 1, 2, and 3 as 3 components. And that's how we've chosen to write this. But when we solve it in finite element format, what we'll do is we'll localize them at a node. So the first 3 terms will be for node 1. The second 3 terms will be for node 2. And the third 3 terms will be for node 3. And it's the same on this side as well, if I can do that. I won't write those out. These are the f terms. So in other words, at node 1, it would be, depending on how we want to do it, maybe it would be velocity at node 1 in the x direction, velocity at node 2, velocity at node 1 in the y direction, and the pressure at node 1. Velocity at node 2 in the x direction, velocity at node 2 in the y direction, and the fluid pressure at node 2. And so you see that these are kind of localized based on the nodes rather than on this previous idea that they would be done, which has gone blurry, with all the velocities first in x, all the velocities first in y, and all the velocities then all the pressures. So that's one of the things that we need to do. So if we go back to this, and I go back down here, so let's look at this. So you recognize some of these features. Again, in terms of what this does, element node, element subroutine. We want to go to the subroutine. We want to be able to send it some interesting data for the elements, and we want to calculate a conductance matrix, a capacitance matrix, or a mass matrix, and then return these back to the main program. That's all it's attempting to do. We have certain nodal coordinate data. We have some data that says something about the material properties. So for the element, we can choose a parameter, and I think in this case this is actually density, and the second term is viscosity. We choose whatever those are, and in this particular case we'll have these elements will be 9 by 9 in size for this stiffness matrix. So that's right. So we pull out the density out of some location in this array. So this is some information. This is a parameter. This is another parameter. This is any parameter that we want to define. And we define it by the form of this element that we put together. And so in other words, out of the third spot, we're taking the viscosity. So let's do what we want to do. I don't recall, you certainly looked at the constant strain, the triangular elements online, and I don't recall whether we used in the video, whether it identified the EGEEfem. But this is basically the coordinate transformations we need to get the A matrix. So this matrix here, for what it's worth, is what we've referred to as the A matrix. Remember, for K second order, it looks something like integral A transpose dA dV. And because it's a triangular element and the distribution of the shape functions that the variable is constant over here, then these terms are all constants, so we can write it as A transpose dA, and the integral dV is just the area of the triangle, delta, times the thickness. Right? And so that's exactly this. That's exactly what this matrix is. So this is the determinant, doesn't matter. So this matrix, by definition, is going to be the A matrix is going to contain terms that look like this. It's going to be a 2 by 3 matrix. I think you can see that. This D matrix is going to be just the terms on the leading diagonal. The D matrix could be something that looks like 1, 0. Usually, we could write this D matrix out as hydraulic conductivity multiplied by 1, 0, 0, 1. Right? That would be the conductance matrix. That would be the constitutive matrix. Because we want to split these things up between the ones that influence X and Y, what we could do is we could make a matrix which is this. For this D matrix. Instead of having this term here, this is the part that operates on dy, and so this is the one which is second order, this is the name of the matrix we're calling here, second order in X. So this is what we've called K2X. If we multiply it by a D matrix, which is, instead of being a 1 here, it's a 0, 0, 0, 1, which is this here. Then we get K second order with respect to Y. And then we multiply them out. A transpose dA is just this term here, I guess, times the area and thickness is this term here, and you end up this. So these are the matrices that represent K1x and K2x and K2y. You'll remember that the K1 matrix was something like integral B transposed VA dV, which, because of the same arguments as this, we can, for a triangular element, we could write as B transposed VA times the area of the element times the thickness. And this term here, just like the D matrix, we could make it, it's a term which includes both Vx and Vy. And so we could choose to make these either 1 or 0. If we made them both 0, it would be null. But if we make Vx 1 and this 0, then it would be the derivative with respect to x, which would be K1x. And the other one is K1y. So the bottom line is that we have, if I zoom back up to what we're looking for, right, we're trying to get a matrix relationship which had the second order terms in it and the second order terms and the first order terms with respect to x and the first order terms with respect to y, and also the transpose of those two. Actually, if you look at this, we know that these are symmetric, and we know that these are anti-symmetric to each other. So actually this matrix relationship ends up being symmetric as well, which is kind of curious. Not sure it matters to us much right now, but that's curiosity. And so then we end up with that matrix equation. And so what ends up now? Okay. So I can't keep both on the same page at the same time. But now we're going to put together a matrix of matrix equations. And so viscosity multiplied by K2, a null matrix, and K1 with respect to x, I think it is. So if we zoom down here, we're now putting these together. This is the big matrix, viscosity times this here is K2 with respect to x plus K2 with respect to y. We split them up. Actually, we don't need to split them up because we never use them. So this term here is mu times this. This is 0, a null matrix. And then this is first order in x. So this matrix here is K1 x. So this is the second with viscosity, a null matrix, and kx. And if we go back up to here, this, and this. And then this is null, and then the repeat of this, etc. You see those. The next line is null. This got messed up because of the carriage return, but this is viscosity times K2 for both x and y, and then this is K1y. So very complicated. It's kind of complicated. So the bottom line is that we end up with a conductance matrix, which is this. This is going to become our term which we're calling KL, lowercase l. And now all we need to do is we need to do what we talked about before, and that is that we need to order it. So instead of being all the values of velocity here in x, all the values of velocity in y, and all the values of pressure, we intersperse them. And so that part here is just the last, the final act in this is this, which is just reordering the columns. I won't go through that. It's kind of complicated. And so that reorders it. So that's it. So that becomes our element that defines this.